Something massive just shook global computing today. A breakthrough emerged that nobody saw coming. A new chip appeared with unbelievable capabilities. It didn't whisper change. It screamed revolution loudly. Experts froze as early reports surfaced worldwide. This wasn't hype, theory, or futuristic speculation. This was a working system already deployed. China unveiled a quantum-photonic monster this week, a processor built entirely around the power of light. Not electrons, not traditional circuits. Pure photon computation. And the performance numbers stunned everyone instantly. Certain AI tasks ran 1,000 times faster. Not 10 times. Not 50 times. 1,000. A speed leap were so aggressive, it felt unreal. Engineers compared it to skipping a whole decade. But the real shock wasn't the speed. It was the fact that it worked practically. Not in a lab, not in isolation chambers. This chip was running inside actual data centers. It powered real workloads across real industries today. The key breakthrough used a photonic wafer design. A 6-inch thin film structure packed with components. More than 1,000 optical parts sat integrated. Light beams traveled through microscopic engineered pathways flawlessly. Every photon carried quantum-style information across the chip. This let parallel processes explode in scale instantly. Tasks that once crawled now finished almost immediately. Light moves faster, cooler, and cleaner than electricity. No heating problems, no energy spikes, no throttling. Data flowed through the chip like liquid lightning. Industries needing extreme performance adapted first. Aerospace simulations accelerated with unbelievable precision gains. Biomedicine models ran faster than previous supercomputers. Financial systems processed patterns before markets reacted globally. The chip transformed workloads across every high-demand sector. Data center engineers noticed something else equally important. The chip consumed dramatically less energy overall. Cooling systems weren't pushed toward dangerous operating limits. Servers maintained efficiency even during maximum performance bursts. This solved one of AI's biggest growing problems. Energy consumption has been rising uncontrollably worldwide. Training advanced models drains enormous power every month. Heat management becomes a nightmare for dense hardware. Companies struggle to afford endless infrastructure expansion. Photonic technology appeared exactly when the world needed it. This new chip didn't require months for deployment. Traditional quantum systems take half a year assembling. This photonic hybrid system installed within 2 weeks. That shock alone sent analysts scrambling for explanations. Its architecture combined classical processing and photon logic. A hybrid engine built for speed and stability. Quantum-style pathways handled parallel operations at insane scale. Classical silicon managed the workloads needing traditional control. Together, they created an unprecedented high-speed acceleration system. Engineers called it a photonic supercluster in miniature, a complete quantum-inspired accelerator packed into one unit. Not prototype hardware, not theoretical white paper concepts. This was real, functional, industrial-grade production hardware. Awards began pouring in within hours of announcement. International conferences highlighted the chip's impossible engineering achievement. Tech analysts compared it to the GPU revolution. Others claimed it started a new computing era. China didn't just build another experimental device, they created a fully integrated production ecosystem. Design, fabrication, packaging, and testing happened domestically. Everything remained inside one unified national pipeline. No outsourcing, no fragmented international manufacturing chains. This advantage terrified competitors across multiple continents. Because successful integration removes the biggest development bottlenecks. It means scale can grow quickly without restrictions. It means breakthroughs convert into products extremely fast. It means the global computing race changed forever. But the most shocking detail was still hidden. A capability buried deep inside the system architecture. A capability that could redefine AI entirely, soon. The real disruption started with manufacturing revelations. Experts realized China wasn't just innovating hardware. They were producing it at unprecedented industrial scale. A pilot line created thousands of wafers yearly. Each wafer produced hundreds of high-performance photonic chips. This output shocked analysts across the semiconductor community. Quantum classical chips normally require delicate fabrication environments. Yields usually remain extremely low for early technologies. Materials like thin-film lithium-niobate complicate production massively. Yet China achieved consistency that rivals mature industries. This changed global expectations overnight without hesitation. Most countries operate tiny research batches only. Their chips sit inside laboratories for experiments. Production rarely exceeds dozens of prototypes per year. Scaling beyond that remains exceptionally difficult today. But China pushed directly into industrial-grade manufacturing. This created something other nations weren't ready for: a complete closed-loop system from start to finish. Design, fabrication, packaging, testing, and integration aligned. Every step synchronized under one unified ecosystem. Nothing relied on foreign plants or external suppliers. This control gave them a brutal advantage. Iterations accelerated faster than global competitors expected. New versions could be tested within days. Manufacturing pipelines updated without international delays. This speed completely reshaped the technological playing field. Meanwhile, the chip's internal capabilities grew clearer. Engineers revealed the architecture handled million-scale qubit analogs. These qubits differed from superconducting quantum bits, of course, but their parallelization delivered unbelievable processing density. Clusters stacked like GPU arrays for scaling. Each added layer expanded parallel quantum-style computation drastically. This turned servers into light-powered supercomputing grids. Photon pathways processed near-limitless interactions simultaneously. Electric-based bottlenecks disappeared from core operations entirely. The chip stayed cool even under extreme loads. Photons simply refused to generate destructive heat. This allowed dense stacking beyond classical chip limits. Data centers operated quieter, cooler, and more efficiently. The bandwidth improvements grew just as impressive. Light carried significantly more information per cycle. Signals compressed better with drastically lower interference. Long-distance fiber-like transmission occurred inside the chip. Error rates dropped, and throughput skyrocketed dramatically. Industries adopted the technology with rapid enthusiasm. AI labs accelerated training models at insane speeds. Aerospace simulations processed thousands of scenarios nightly. Biomedicine generated molecular models in record time. Finance executed advanced pattern detection instantly under pressure. Every sector facing computational bottlenecks embraced photonics. The chip attacked problems GPUs struggled with deeply. Massive parallelism gave undeniable advantages for AI. Latency shrank to levels previously called impossible. Engineers integrated electronic and photonic co-packaging soon after. Both systems combined onto unified next-generation wafers. This eliminated connection overhead between complementary components. The chip became easier to deploy globally. Still, independent verification became necessary for validation. Researchers wanted neutral performance tests and comparisons. Early numbers shocked enough people to raise doubts, but deployment across industries suggested real-world reliability. Other companies reacted quickly to the announcement. NVIDIA accelerated investments into optical technologies immediately. They understood the future was shifting toward photonics. Power consumption had become a rising worldwide crisis. AI advancement demanded faster, cooler hardware urgently. Global competition heated up across multiple nations. Google expanded superconducting quantum research even further. IBM doubled efforts on quantum error correction systems. European groups pursued silicon photonic alternatives aggressively. Every region committed to their strongest technological bets. But China pushed beyond research-level projects entirely. Their photonic computers left the lab this year. They entered data centers as operational machines. This milestone shifted global attention instantly and forcefully. Quantum computing was no longer academic theory only. Hybrid systems became the new strategic direction. Photons handled massive-scale computational loads internally. Classical chips maintained structure and system stability. This blend delivered unmatched performance numbers globally. Engineers warned this was just the beginning. The next generation would push speeds even further. Stacked photonic grids might dwarf today's supercomputers. Energy efficiency could reshape everything about AI. But beneath this breakthrough hid a deeper shift. A transformation that could alter global technological power. A change that might redefine future supercomputing entirely. And the consequences could echo for decades ahead. The deeper implications started emerging very quickly. Researchers realized this wasn't just faster computing. It was a structural shift in global power. Control over photonic technology meant strategic dominance. Every nation understood the stakes instantly and completely. For decades, silicon dictated the world's digital hierarchy. Whoever controlled fabrication controlled technological evolution. Now photons threatened to rewrite that hierarchy entirely. Light-based processors didn't follow old limitations anymore. They scaled faster, cooler, and dramatically more efficiently. This changed the meaning of computational supremacy forever. Supercomputers suddenly looked outdated compared to photonics. Even GPU clusters struggled beside quantum light architectures. The performance gap grew wider every passing month. Behind closed doors, governments evaluated long-term consequences. If photonic grids became mainstream infrastructure worldwide, countries without production lines risked falling dangerously behind. They wouldn't just lose performance, they'd lose independence. Access to advanced computing determines future military readiness. It shapes economic modeling and strategic global forecasting. AI models define modern influence across everything today. Predictive systems enhance logistics, finance, and national planning. Larger models demand stronger computational backbones constantly. Whichever nation trains fastest ultimately leads the world. That's why this breakthrough triggered worldwide alarm. Analysts compared this moment to nuclear transitions. Others compared it to the Internet's earliest revolution. Some said it surpassed both in overall importance. Because intelligence, not weaponry, defines future geopolitical strength. Meanwhile, photonic architecture kept revealing new abilities. A revolutionary feature stood out among researchers globally. Photon distances inside the chip were unbelievably short. This compressed architecture reduced latency to microscopic scales. Fewer millimeters meant higher accuracy and faster throughput. Traditional processors lose energy over longer distances. They generate heat, noise, and corrupted signals. Photonic chips nearly eliminated those destructive side effects. Information moved cleanly through ultra-tight optical pathways. This resulted in drastically lower error margins. Quantum-style interference became significantly easier to control. Bandwidth surged far beyond classical chip capabilities. Engineers measured improvements they previously considered unrealistic. These changes enhanced algorithmic stability at large scale. AI systems trained more consistently without heavy distortion. Massive datasets moved rapidly with almost perfect clarity. Unstable workloads stabilized like never seen before. This allowed unprecedented growth in model sizes. Algorithms previously impossible now became fully achievable. Future systems could reach unimaginable levels of complexity. Next-generation AI might operate closer to real cognition. But competition didn't sit idle, responding slowly. Tech giants accelerated research pipelines at breakneck speed. New partnerships formed between companies and laboratories. Quantum startups received instant attention and heavy funding. Governments launched programs prioritizing photonic advancement globally. Everyone aimed to challenge China's sudden leadership. But China held the advantage of early deployment. Their chips weren't simply theoretical prototypes anymore. They ran inside national data centers right now. They powered companies, industries, and research institutions today. The rest of the world still tested prototypes. They studied theory papers and beta-stage hardware. China operated functioning machines built for real workloads. This gap hinted at enormous future consequences. A technological divide growing larger every single month. Meanwhile, engineers discussed scalability concerns worldwide. Could photonic grids expand without unpredictable failures? Could manufacturing maintain consistency across entire wafer batches? Could integration remain stable under global deployment pressure? Surprisingly, early results showed stable long-term patterns. Photonic chips performed reliably across multiple industries. Their structure resisted thermal stress exceptionally well. Their lifespan exceeded expectations across endurance testing phases. This validation signaled something very important globally. Photonic quantum acceleration was ready for mainstream adoption. Not next decade, not next year. Right now, industries prepared to restructure infrastructure around light. Cloud platforms assessed new architecture requirements immediately. Telecom providers considered photonic upgrades for future bandwidth. AI research groups redesigned algorithms for photon pathways. Supercomputing centers prepared for hybrid processing systems. A new computing era emerged before anyone expected. But the next revelation would shake everything harder, because researchers discovered a capability they hadn't predicted. A function hidden deep within the photonic architecture. A feature that could transform intelligence as we know it. The final revelation hit harder than expected. Researchers uncovered a hidden capability inside the chip. Something deeper than raw power or speed. Something that rewired expectations for future intelligence. The photonic architecture wasn't just accelerating processes, it was enabling entirely new computational behavior. Light-based pathways created dynamic interference patterns constantly. These patterns resembled primitive forms of reasoning. They adapted, reorganized, and recombined during heavy tasks. This wasn't consciousness, but something intriguingly close. A structural foundation for higher-order machine intuition. Traditional processors follow fixed deterministic electrical routes. Photonic systems evolved calculations through flowing light behavior. They acted more like thinking environments than circuits. Engineers noticed tasks completing with unexpected efficiency. The chip discovered shortcuts during algorithmic workloads. Certain operations ended faster than predicted mathematically. This hinted at emerging quantum-inspired decision strategies. Strategies difficult to replicate using classical electronics. This discovery stunned global research communities instantly. Because intelligence grows from adaptive pattern resolution, and these chips naturally formed adaptive optical patterns, patterns that shifted with tasks automatically and intelligently. If scaled further, machines could approach reasoning systems, not training-based reasoning, but hardware-level reasoning structures. A kind of computational intuition built from photons, something silicon never achieved across decades of experimentation. Suddenly, the global race transformed dramatically. It wasn't about faster chips anymore. It was about the birth of new intelligence. A hybrid intelligence mixing photons and algorithms together. A form of computation with unpredictable potential pathways. Nations prepared for a future shaped by light. Corporations scrambled to secure photonic supply chains. Universities redirected entire research programs toward optical computing. Funding surged into labs chasing similar breakthroughs. The momentum felt unstoppable and absolutely fierce. But uncertainty grew alongside the rapid adoption. People worried about technology outpacing human understanding. What happens when computation grows unpredictable internally? What happens when logic blends with quantum dynamics? What happens when AI systems evolve beyond monitoring? Experts warned about transparency becoming difficult eventually. Photon interference can create opaque decision regions. Explaining those regions may become nearly impossible. Accountability depends on understanding how machines think. Photonic systems challenged that requirement deeply and directly. Others saw enormous promise rather than danger. Medical simulations could revolutionize global healthcare instantly. Aerospace planning could prevent catastrophic mission failures. Climate modeling could reach unprecedented accuracy worldwide. AI could analyze crises before they escalate further. Entire industries could operate safer and more efficiently. The divide between fear and excitement widened quickly. Some believed photonic intelligence would uplift humanity entirely. Others believed it would reshape power unpredictably worldwide. Both viewpoints carried significant truth and heavy weight. Meanwhile, China continued advancing production pipelines aggressively. New fabrication wings prepared for expanded yearly output. Industrial integration programs accelerated across multiple provinces. Government agencies reinforced photonic national strategies stronger. This coordinated push solidified long-term leadership globally. International competitors responded with renewed determination. The United States boosted optical research funding drastically. Europe invested in silicon photonic hybrid platforms aggressively. Japan increased quantum light hardware development initiatives. Every region prepared for this technological shift, but China remained months, maybe years, ahead currently. Their chips weren't plans or prototypes anymore. They were active engines powering national computation. They were tools already transforming industrial output dramatically. Researchers believe the next generation will be monumental. Chips could reach unimaginable computing densities soon. Stacked photonic grids might accelerate AI exponentially. Hybrid reasoning systems could operate beyond human prediction. Data centers could shrink while gaining enormous capability. Every advancement pushed humanity toward a new frontier. A frontier where intelligence becomes cheaper and faster. A frontier where photons shape digital civilization directly. A frontier where computing feels more alive than mechanical. This week marked the birth of that frontier, a tipping point that cannot be reversed again. Computing crossed into its next evolutionary phase permanently. The age of photonic intelligence had officially begun, and the world must now brace for everything coming next. Because the future won't arrive gradually anymore. It will arrive at the speed of light.